Welcome. This is 48I video 1 and we're going to start talking about the energy of a system. In the whole chapter we'll talk about the work done by a constant force, and then we'll talk about a thing called scalar product, and then we'll talk about the work done by varying forces, and then we'll talk about how work causes a change in kinetic energy, or work causes a change in the gravitational potential energy, or work causes a change in the spring potential energy. And the important thing to understand here is we're defining kinetic energy, we're defining gravitational potential energy, and we're defining spring potential energy. And we'll use those in future chapters. So we say the work done by a constant force. We say work is the displacement of a force through a distance. It's not any old force times any old distance. We need the force and the displacement to be in line, or we need the component of the force that is in line with the displacement, or the component of the displacement which is in line with the force. So if we look down at this diagram, here I have a force, and it's not in line with a displacement. So I need to take the component of the force that is in line with the displacement, and I get F cosine theta times D. Alternatively, I have a situation here where I have a force that's not in line with a displacement, but I take the component of the displacement that is in line with the force, and I get F times D cosine theta. Can you see in both cases we have the same numerical value? We have an F multiplying a D multiplying the angle between them. So it doesn't matter which one we do. Now, it turns out that when you get vector A, if you have vector A and vector B, and if you have the magnitude of A times the magnitude of B times the cosine of the angle between them, we call this a scalar product. And we designate it as A, big dot, B. And so in this case, we can say work, and this should not be a vector. I'm so sorry about that. That note needs correcting. This should be a scalar work, because work is a scalar, is equal to the force scalared or dotted with the displacement. So we say the work done by the force is a scalar quantity and is measured in joules. If the force is perpendicular to the direction of motion, no work is done. So if the force is my lifting force and it's perpendicular from my displacement, I'm carrying something across a room, my lifting force does no work. That might seem odd, but that's the problem with using biology to inform our physics. If my force and my displacement are in line, or if they are mainly in line, we have positive answers. If my force and my displacement are completely in opposite directions, or they are largely in opposite directions, then we have negative answers. So if the angle is between 90 and 0, we get positive answers. If the angle between them is over 90 to 180, we get negative answers. A negative work means that we'll be taking energy out of our object. So work is done by a force which acts on an object, and the action of work is to put more energy into the object or take energy out of the object. So a bit more on these so-called scalar products. So we have multiplying vectors is not the same as multiplying scalars. we can specify a so-called scalar product, sometimes called a dot product, which is vector A dotted with vector B is the magnitude of A times the magnitude of B times the cosine of the angle between them. And we could also define a vector product, which is vector A, we say crossed with vector B, which gives me a vector answer, which is vector C. Now, the magnitude of C is the magnitude of A times the magnitude of B times the sine of the angle between them. We'll use this later on when we start talking about torque. For the moment, we're talking about work, so we use the dot product. The dot product is appropriate. A scalar product is commutative, so vector A dotted with vector B is the same as vector B dotted with vector A. A scalar product is distributive, so vector A dotted with vector B plus vector C is vector A dotted with vector B plus vector A dotted with vector C. If A is perpendicular from B, then our answer is 0. If A is parallel to B, then our answer is simply vector A times, is simply the magnitude of A times the magnitude of B. If vector A is anti-parallel to B, then our answer is minus the magnitude of A times the magnitude of B. If we think about ijk vectors, then unit vector I dotted with the unit vector I gives me 1. Unit vector j dotted with unit vector j gives me 1. Unit vector k dotted with unit vector k gives me 1. They're both one unit and they're parallel to each other. And I dotted with j is 0 because they're at 90 degrees, and I dotted with k gives me 0 because they're at 90 degrees, and j dotted with k gives me 0 because they're at 90 degrees. But most of the time we're going to have vectors which are not lined up or perpendicular. So we can take two three-dimensional vectors. Let's just realize this is a vector which has an arbitrary position through space, and a second vector which has an arbitrary position through space, and we can find their scalar product. And the way we do it is we take the component of I times the component of I, and we add that to the component of j multiplied by the component of j, and we add that to the component of k times the component of k. So we get plus 2 times plus 5 added to plus 3 times plus 6 added to plus 5 times minus 7, which gives me plus 10 added to plus 18 added to minus 35, gives me minus 7 units. And if this was a work problem, if A was force and B was displacement, I would have minus 7 joules, and that would be taking energy out of my object. So maybe it would slow down. Let's do some examples. So we go back somewhat to the beginning and we say, okay, we have a 4 kilogram and we're going to move it 3 meters, and it's going to be pulled by 6 newtons, and that's going to be at 20 degrees. So it says a student pulls a 4 kilogram block 3 meters across a level rough floor by applying a steady force of 6 newtons at 20 degrees above the horizontal. How much work was done by her 6 Newton force? It's important to realize that it's the forces that are doing the work, and so I don't even have to worry about other forces. I don't need to worry about the weight and the normal force, because they're not the forces I'm interested in. I'm only interested in this 6 Newton force. So I can say the work done is equal to, it's going to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between. And by the way, this is equal to the vector force scalared or dotted with the vector displacement. In this case, I'm going to use the magnitudes. So I say my work done is equal to this is going to be 6, and this is going to be 3, and this is going to be cosine 20. Can you see how, because I wrote down the equation in that form, I didn't even have to visualize whether I was doing the component of the force in line with the displacement or the component of the displacement in line with the force? So I say this is going to be 6 times 3, enter, times the cosine of 20, enter, and I get 16 plus 16.9 joules. 16.9 joules. So there's a classic question on this. Let's look at the next thing, and this is using IJK vectors. So a force of 3I minus 6J plus 2K newtons. I don't know what direction that is. I'm just going to show it schematically. 3I minus 6J plus 2K newtons acts to displace a 5 kilogram object through this displacement. So this is my displacement, and this is going to be minus 4I plus 2J plus 4K meters. And we want to know how much work was done by this force. So we say, well, the work done is equal to F scalared or dotted with D. Let's just complete it just so we keep remembering it, which equals F times D times the cosine of the angle between. We have no idea what the angle is, and working out the magnitudes would take time, but by far the easiest way to do this is to say that work is equal to 3I minus 6J plus 2K dotted with or scaled with minus 4I plus 2J plus 4K. And then the way we do this is we multiply the coefficients together. So this would be 3 times minus 4 added 2 minus 6 times plus 2 added 2 times 4. So our work is equal to minus 12 added 2 minus 18, minus 12 added 2 plus 8. So work is equal to minus 12 added to minus 12 is minus 24 plus 8 is minus 16 joules. So the answer will be minus 16 joules. The negative indicates that the energy has been taken out of the object. So the 5 kilogram mass would have less velocity or would be lower in a gravitational field. Let's look at this next one. So in this example here, we have a 6 Newton force pointing in the positive y-axis. Well, that's going to be upwards, and that's 6 newtons, and that's going to be my force. And then I have a 5 kilogram mass, and I have a 3I minus 2J plus 4K meter displacement vector. And, well, I want to find the work done by this force. Well, work is equal to the vector force scalared or dotted with the vector displacement. And that equals the magnitude of the force times the magnitude of the displacement times the cosine of the angle between. And I have two choices here. I can try to find the magnitude of the displacement and the angle between the force and the displacement and use the right hand side of the equation. That's hard. Finding the angle between the vector force and the displacement is not trivial, it's long. Or the other way is I find a vector for the force and then use the middle bit, the dot product. The vector force is actually easy to find because it's a magnitude with a simple direction, positive y-axis. And I know that this vector force would have no I component. It would have a plus 6j component because that's the y-axis and it's positive, plus 0k newtons. So a 6 Newton force pointing along a positive y-axis is a 0I plus 6j plus 0k. A 6 Newton force pointing along a positive x-axis would be a 6I plus 0j plus 0k. Because it's in the axis, we know there's nothing in the other components and it's all on either the I, the j or the k. It's easy to do when it's like this. So I say, oh, well, my work is equal to 0I plus 6j plus 0k scaled with 3I minus 2j plus 4k. So my work is equal to 0 times 3 added 2, 6 times minus 2 added to 0 times 4. So my work is equal to 0 added to minus 12 added to 0, which equals minus 12 joules. And there we have it.